Hold your hand out and imagine grabbing a tennis ball. Now squeeze it with as much force as you possibly can. Just let go and do it again. Try to keep that up for 100,000 reps today. Within a few minutes, your forearm will lock up. The cells run out of available energy, metabolic waste floods the tissue, and your muscles physically fail. Yet the exact amount of force it takes to squeeze that tennis ball is generated by your heart on every single beat. It hits that 100,000 rep mark every day, reaching well over 3 billion beats in an average lifetime. The heart is a muscle built from the same basic proteins that make up your biceps and forearms. Biologically, it should fatigue, cramp, and require rest after a heavy workload. It doesn't, and it's not because of a hidden rest period between beats. To survive lifelong exertion, the heart operates on a different class of internal cellular machinery than the rest of the body. The first distinction is found in how a muscle actually knows when to move. When you squeeze your hand, your brain sends an electrical impulse down your spinal cord to trigger the contraction. That pathway requires active, voluntary control. The heart bypasses that system using autorhythmicity. The SA node generates its own electrical spark, maintaining a steady rhythm without the brain. Linked by gap junctions, this initial spark spills across the cells, locking the entire heart into one synchronized wave of contraction. By removing the brain from the trigger process, the heart eliminates central nervous fatigue. The signal never stops because the heart is driving itself. Triggering the movement is only the start. The muscle still needs the energy storage to execute that trigger. This shows the energy capacity of different muscle types. In skeletal muscle, only 1 to 2% of the cellular volume is dedicated to mitochondria, the structures producing energy. In cardiac tissue, mitochondria take up a staggering 35% of the internal space. Standard muscle acts like a rechargeable battery, drawing down limited reserves and needing downtime to recover. This density transforms the heart into a real-time combustion engine, producing energy as quickly as the muscle consumes it. Even with that energy, the heart has to manage the waste. When skeletal muscles are pushed to their limit, metabolic byproducts build up, causing a burning sensation. Under heavy load, limbs run low on oxygen and produce a waste called lactate. As it accumulates, the tissue becomes too acidic to function, forcing the muscle to shut down. The heart avoids this debt by maintaining constant oxygen delivery through its own dense network of coronary arteries. But it also uses a second strategy. The heart consumes lactate. It pulls it out of the blood and burns it as fuel alongside glucose and fatty acids. It resists fatigue by powering itself with the exact chemical waste that causes the rest of the body to fail. If this tissue is immune to fatigue, why aren't our arms and legs made of it? Because cardiac cells are interconnected and fire automatically, having biceps made of heart muscle would result in uncontrollable movement. Your limbs would spasm involuntarily, making purposeful actions impossible. There is also a metabolic cost. This chart compares the energy burn of different tissues. Cardiac muscle is incredibly expensive to maintain, consuming energy at a rate nearly 35 times higher than resting skeletal muscle. Replacing all your skeletal muscle with cardiac tissue would cause your daily caloric needs to skyrocket. You would have to consume vast amounts of food every day just to keep your body from starving. The 3 billion beats of a human heart are made possible by a specific evolutionary trade-off. This energy-intensive cellular architecture is restricted to a single organ because the energy required to run it is too high for the rest of the body to sustain.